Hey everybody, it's Mr. N, and we are going to do the 5-1 lesson in our book. This deals with areas and distances. So it's the beginnings of how to find the area under the curve and some distances here. So let's take a look at what we got. We'll start off with a lot of talking, a lot of notes, and then we'll get into the examples. So let's start with this. Okay, finding the area under the curve. So basically, we know how to find areas of things. We know how to find an area of a circle. We know how to find the area of a triangle. We know how to find the area of a rectangle. We've been given formulas to do this. But what if it wasn't a shape we are accustomed to? What if it wasn't a circle? Right? What if it wasn't a circle? What if it wasn't a triangle? What if it wasn't a rectangle? What if it was some weird shape like this, where I'm finding the area from this point to this point underneath this curve? Well, there's got to be a way to do it. So this is a common theme in calculus. And those of you that had me for geometry with the area on the curve, you thought you got away from it? You thought you were all done with it? Nope, it's back. Here we go. Now, since this is a common theme, we can date it back to way, way back. And Archimedes, it's commonly referred to as the area problem, finding these areas. He used a method called exhaustion. And then Newton and Leibniz also developed their methods. And to find the area under the curve from A to B, you need to develop some sort of system, some sort of something. In other words, let me explain to you kind of the thought process here. Suppose I had some sort of rectangle, right? We know that a rectangle is the length times the width, but there are other methods of doing this. Suppose I cut this into two triangles. I could add the area of one triangle and the area of another triangle, and I'll get the same value in the end for the area of this rectangle. So we knew how to do this with various objects, and in fact, we took this a little further. Suppose you had something like a pentagon, and we just broke this up into triangles like this, and we found the area of each of these three triangles and added them up. So we have methods of breaking up things that we don't know how to find areas of into ones that we do. So that's how we were able to develop the formulas. So you have these formulas, but what if you had some sort of shape that looked like this, right? I mean, you could start maybe trying to break it up into ellipses or circles or whatever, but it gets really complicated. So we have another method of doing it called finite sums. Now, this is a rectangular method, and what we do is, suppose I had this curve. We'll come back up to this one up here. What I can do is I could break this up into rectangles like this and find the area. Oops, that last one wasn't so good. I missed. I wanted to do it down here. And then find the areas of each of these rectangles I created, and it would give me an approximate area under the curve. Now, the more rectangles I make, the better my approximation is, right? And I know a rectangle is length times width, so I've tried to keep it with an easy shape. You can use any shape you want, but let's stick with rectangles right now. So this rectangular method, suppose you have this curve, you can find the area under it, you can make rectangles to approximate and find them. Now you should notice something here. As I do these rectangles, I'm going to pick a point on the curve, I'm going to go across, and I'm going to come down. Pick a point on the curve, go across, come down. Pick a point on the curve, go across, come down, and I've made these rectangles. Now, I know the width and the height of each of these rectangles, and I can use that and find the area of each of them, area of 1, area of 2, area of 3. So the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3, and get an approximate area under the curve. But what do you notice? What do you notice? You should notice something. Wait. There's a big old gap here. There's a big old gap here, right? Well, yeah, there's going to be gaps, so it's just an approximation. If I drew my rectangles smaller, such as in this one, notice these gaps are smaller as well. I can make my rectangles super small and make the gaps even smaller. But you'll also notice something else. The way I've made these rectangles, this right now is an under approximation, right? Because I don't have these. I've got these gaps that I haven't filled in the area for. So let me erase this. And what if I drew my rectangles in this manner? What if I started from the right side, right, and made a rectangle? Then the right side and made the rectangle this way. The right side and made the rectangle that way. So now I have this and this, but now look what I have, an over approximation. So it depends on how I draw my rectangles. I can even draw them so that they're at the midpoints here, like that. I could draw them, they're at the right, I could draw them on the left, but one thing that will stay common, and you will notice, is the more rectangles you make, no matter what method you use, whether I draw these from the left points or the right points or the midpoints or however, the more rectangles I make, the better my approximation. So let's look at this one. Notice on this one, look at all the rectangles I made. That's going to give me a pretty good approximation of the area under the curve. So, but guess what? The more rectangles you make, the more work it is, the more exhausting the method is. In fact, you can go as far as making an infinite number of rectangles, right? We can do that, and that would be a limit. We'll take the limit as the rectangles approach infinity. We know how to do limits. We can solve problems like that. So that was the method that they came up with to find the areas under the curve. So let's take a look at the next page we have here. All right, so here we're going to talk about different types. If I have an increasing curve or a decreasing curve, if I use left endpoints, right endpoints, or middle. So this is almost like a chart so that you can kind of see what's going on here. And if I have, you can go like this. If I have an increasing curve, in other words, the curve is going up, and I use left endpoints, that's this situation right here. The curve is going up, and I'm using a left endpoint to draw a rectangle. I will get an underestimation because I will have this gap right here. If I use left endpoints and I have a decreasing curve like this right here, this curve is going down, it's decreasing this part of the curve, I will get an overestimation, so I'll have all this extra area. And it's opposite if I use right endpoints. If I use a right endpoint and make a rectangle, okay, and the curve is increasing, I'll get an overestimate. If I use a right endpoint and the curve is decreasing, such as here, I will get an underestimate. But check this out. If I use midpoints, if I take it from the middle, whether the curve is increasing or decreasing, I cannot determine if I'm going to get an overestimate or an underestimate. So, having said all that, let's try one. Let's just try a basic one. Over here it says find an approximation of the area under y equals x squared from 0 to 1. And here's our additional information we need. We need to be told in this particular problem, since we're doing an approximation, use left endpoints. Okay, we'll use the left endpoints. And we have rectangles of widths of 1/4. So let me first graph this. So here's what I got. I'm going to do a nice big graph. Hopefully you guys have graph paper to do this. I'm going to draw my curve on here. Now, I'm going y equals x squared, so if I put in from 0 to 1, so when I put in 0, I get 0, and I'm going to put 1 way out here. When I put in 1, I'll get 1 way up here, and you know that this is parabolic, so it's going to look like this. And we have a curve that looks something like that, okay? Now, I wish I could have drawn it a little straighter, but that's a little cleaner, but that's okay. All right, so now I've got my curve that looks like this, and I'm going to use left endpoints. What does that mean when I'm using left endpoints? That means I'm going to pick at 0, I'm going to pick here, and I have widths of 1/4. So I'm going to go out to 1/4. Okay, let's do this in another color here. Let's go to 1/4 because I'm going to use green for my rectangles. And then there's 2/4, right? Then there's 3/4, and then there's 4/4, which is 1. So this is the 4/4. I'm out here at 1. And I'll just put that in block as well. Okay, so now let's draw the rectangles. I'm starting from the left side. So look, check this out. My first rectangle, how many rectangles will I have? Think about it. If I'm going from 0 to 1 in 1/4, I'll have 4 rectangles, right? So over here, I'm going to start at, look at my first rectangle, has no height whatsoever. So my second rectangle will start here, go across, and come down. My third rectangle will start there, go across, come down. My fourth rectangle will start there, go across, come down. Now, you know, now I can draw these in like that. You know I'm going to get an underestimate. This is clear that I'm going to get an underestimate. There's a lot of area in here that I have not taken into account for. So this is a huge underestimate for this particular problem. But let's take a look at what we have, and let's do this. So this is rectangle 1, this is rectangle 2, this is rectangle 3, and this is rectangle 4. All right, so the area is going to be approximately each rectangles, right? So the first rectangle, and I'll draw it out here, has a length or a width of 1/4 and a height of 0. Plus the second rectangle will have a width of 1/4. And how am I going to find out the height of this one? Well, take a look. This will give me this point right there, right? The equation itself will give me that value, that point I'm looking for. So all I got to do is plug it in there, and we'll do that. So if I plug y equals, and I'm over here at 1/4, that's going to be my height, and I'm looking at this part right here, 1/4 squared, this will give me 1/16. So this height on this side was 1/16 right there. Then I need this height right there. That's at 2/4. So y equals 2/4 squared gives me 4/16. So the next one will have a width of 1/4 and a height this time of 4/16. Plus my last rectangle, we know will have 1/4, and now I'm looking for this height, y equals 3/4, and I'm going to square that. I will get 9/16. So this height this time on the last one is 9/16, because I'm using the left endpoints. So the area will be approximately 0 plus, over here when I multiply these, I'm going to get 1/16 times 1/4 plus 4/16 times 1/4 plus 9/16 times 1/4. Now some of you see a pattern here. Oh, can't you just take the 1/4 out of each of them and put it out in front? Yes, when we develop our formula, we will. So the area, adding all these up, will be approximately 7/32, which is approximately 0.21875. Now, what if I used, this is left endpoints, right? What if I used right endpoints? Well, how does this change it? Well, the area will be approximately, now if I use right endpoints, I'll draw it out over here just real quick for you. My first one will be at 1/4, and it'll look like this. My second one will be at 2/4, and will look like that. My third one, this goes here, will be at 3/4, will look like that. And look at my last one here, this is at 1, here's 1, will be at 4/4. So my values for the height will change. Now they will change because I'm using the right side. Again, if you look at it over here and compare, okay, look at it right here and compare, I'll be using the right side, so the rectangle this way. Rectangle. So this time I'll get an overestimate, and I'll start shifted over 1, but I'll finish here. Notice on this one, I had my 4 rectangles. I started at 0 and finished at 3/4. If you do right endpoints, you will start shifted over 1, but finish at the end. So over here, this will end up being, the width is 1/4, and then the height will be with the 1/4 squared, which is 1/16. Then the next one, the width will be 1/4, the height will be 4/16, Then the next one, the width is 1/4, and the height is 9/16. And then the last one, the width was 1/4, and the height will be 1 squared, which is 1. And this will give me an approximate of 15/32, which is approximately 0.46875 square units. I forgot to put the units on this, square units. All right, so now let's generalize this process. Suppose I had over here strips that were 1/n in width. Over here I said they were 1/4 in width, but what if I just generalize it and make this, instead of 1/4, just 1/n? The height would be, you plug 1/n into your equation, 1/n squared. So the area equals the length times the width, or in our case, we like to call it the height times the width for all the rectangles. So this is the width right there. So let's say that this is our width, this would be our height. The second rectangle, the third rectangle, etc. This is the nth minus 1 rectangle. So there's our height. And this is our nth rectangle. So we have a summation that we're going to do here. So if I multiply these out, what I can do is they all have something in common. I can reduce this by taking out this 1/n, and then they'll all have this 1/n squared in common. When I take that out, I'll end up with 1 squared, 2 squared, 3 squared, n minus 1 squared, and an n squared over here. So here is how you can think of it with the subdivision from 0 to 1 with rectangles 1/n. So I end up with this formula that I've generalized it to. Well, this is the summation right here of just n squared. And we have a formula for this summation. You learned in previous courses this formula, and this formula is right there. So I can substitute that in, because now I have this summation formula, and I'll end up with this 1/n, 1/n squared, and then the summation formula. I can clean all this up, and now I have a formula to find the area from 0 to 1 of this particular equation, this scenario. Now, I want to get an exact area, so what I need to do is to take a limit. So let's go to the next page, and let's move this up over here so we can see that I've taken a limit from n goes to infinity of this area, and I've plugged the values in over here. So let's just do that again so I can show you, because it was on the previous page. I had 2n squared plus 3n plus 1 over my 6n squared. The limit as n goes to infinity, remember we're just going to take a look at these large coefficients, and that gives me 2/6, which is 1/3. So this is the exact area underneath that curve from 0 to 1, where y equals x squared. From 0 to 1, that is the exact area underneath the curve. So here's another way we can talk about this and do this. Suppose I had my delta x is what I'm going to call, which is the width of the rectangles. And the delta x will end up being this interval from 0 to 1 divided by the number of rectangles you want, n. So in this case, we're going to say the interval is 1 minus 0 over n, because I'm not going to specify a number of rectangles. I'm going to keep it open-ended. So then we have f of x sub I, and then the I will just be each rectangle I'm talking about. So the first one, the second one, the third one. So x sub 1 would be the first iteration, f of x sub 1 equals x squared, and we're plugging in values as I changes, where I is going to keep going on and on. So we're plugging in I delta x, thus f of x sub I equals I delta x squared. This is as I changes, because this is my equation, y equals x squared. That's where I have that from. Okay, so then we want to take this limit. So we want the limit out to infinity, the limit as n goes to infinity of this summation right here. This is my summation, f of x sub I times delta x. So this is my height, this is my width. I want the sum of the heights times the widths. And our equation is right there, so I can substitute that in with what I found up here. So the limit as n goes to infinity of the sum from I equals 1 to infinity, because my I is all the rectangles and I want an infinite sum of rectangles, times delta x, which is my width, this was my height, equals the limit as n goes to infinity, and now I'm going to plug this in. I get I squared times delta x squared times x. Actually, all I did was work this part out. Delta x is constant. That's our change in x value. We're going to put it on the outside. So the limit as n goes to infinity of delta x cubed now equals the sum from I equals 1 to infinity of I squared. And we know this summation. This is the summation of n squared, and that was the formula we came up with before. And our delta x is the width, which is 1 over n, and that's what we came up with up here, 1 over n. And now I'm going to plug that in as well. I work the whole thing out. I get the same exact formula as I did up above, and I'll get 2/6, which is 1/3. Now, on this alternate method, I'm taking right endpoints. If I were to use left endpoints, then it would be this value, I, minus 1. It shifts it back, right? Because if I said 1/4, like we did in the first one, that would put me at 1/4. But if I wanted to go back to 0 and use left endpoints, I would have to say 1/4 minus the 1/4. So in this case, I would have to say I minus my first iteration to get me back to 0. That would be left endpoints. So we can define all this. We can say the area of the region S that lies under the graph of the continuous function is the limit of the sum of the areas of the approximating rectangles. So basically I'm saying I'm going to take an infinite amount of rectangles, find that summation, and I will get the area. So R sub n is equal to the sum of the areas of the rectangles in terms of n, and delta x will be our width. Now, here are some formulas, again, get it, some formulas. These are the summation formulas that you will encounter, a lot of them, but there's going to be some where we cannot do it, and I'll talk about those in a minute. Okay, so the sum of I is this, the sum of I squared, the sum of n cubed, the sum of n to the fourth. These are basic ones. Some basic rules to remember: the sum of a constant, you can put it out in front. So that you end up with n times c. The constant comes out in front, and then you just end up with this summation. And then if you have two things that you're summing, you can distribute it and do it in this manner. So it is a distributable function. All right, so let's put this into this example, and let's see what we could do with this. Let me slide this up a little bit. Find the area under the curve of this equation using 10 rectangles. Okay, so this equation, if I graph this out real quick and sketch it out for you guys on the side over here, is going to be a function that looks like this. And it will go up and back down, and over here from 0 to 1, when I put in 0, I get 0. When I put in 1, I will get 1. And I'm going to do 10 rectangles. And I should have said here, use right endpoints is what we're going to do on this one. We're going to use right endpoints. So my delta x is going to be b minus a over n. So that is my formula from up above that we talked about. This is a, this is b. So this will be 1 minus 0 over 10 rectangles. So 1/10 is my iterations on the rectangles. 1/10, 2/10, 3/10, all the way out to 10/10. So the area is going to be the sum of my rectangles. So the sum starts at I equals 1 and ends at 10. And this is my f of x sub I, which will give me the height, times my delta x, which will give me the width of each of these rectangles. So you could think of it as it's delta x times all your heights, right? Because the delta x will be consistent. So the area will be approximately, and I'm going to take the delta x out, so this will be delta x times all these heights, right? So let me write it down here like this, like I wrote it. So that'll be 1 over 10. Now here I'll have f of x sub 1, f of x sub 2, all the way out to f of x sub 10. And the reason why I started here is because I said right endpoints. If I would have said left endpoints, this would be f of x sub 0, and then I would end at f of x sub 9. Okay, so the area will be 1/10. Now, f of x sub 1 will be f of 1/10. Okay, so this is f of 1/10 plus f of 2/10 plus f of 3/10, f of 4/10, f of 5/10, f of 6/10, f of 7/10, f of 8/10, f of 9/10, and f of 1, which is 10/10. Okay, substituting all these values in, I will get 1/10. And now I'm plugging it into my equation right here. 2 times 1/10 minus 2 times 1/10 squared. And I'm going to do this for every single one of these. And I'll just save you the hassle and tell you what these all end up being. And these all end up being, the first one is going to be 18 over 100 plus 32 over 100 plus 42 over 100 plus 48 over 100 plus 50 over 100 plus 48, and you'll see the pattern here because this is parabolic, plus 42 over 100 again, plus 32 over 100 plus the 18 over 100, and then this will be 0 at the end. So the area will be approximately 0.3325, which we ended up with as a fraction was 33 over 100 on this particular problem, and that's square units. All right, let's see what we got next. All right, for this next problem, it says find the area under the curve of y equals x cubed from 1 to 4, and then we are asking for right endpoints and 6 rectangles. Quickly sketching out the curve, let's do that, and we end up with this situation. And this is x cubed, so from 1, we'll get a value of 1, and over here out to 4, we'll get a value way up here, and I'm just going to put it up there, but we're looking at this part of the curve, okay? And I need 6 rectangles, right endpoints, so n equals 6. So delta x equals b minus a over n. So this is 4 minus 1. There's a, there's b, over n, which is 6, which gives me 3 over 6, which gives me intervals of 1/2. So that means I'll be at 1, 1.5, 2, 2.5, 3, 3.5, and 4. And since I'm doing right endpoints, my rectangles will start at 1.5 right there and look like that. That's how these rectangles will look. Okay? So this is the right endpoint. So I will get, in this case, since it's increasing, I will get an overestimate. All right, so let's put this area together and see what we can do. Over here, we know the area will be the sum of the rectangles, right? And this will be approximately my delta x, which is my width, right, for each one, times the height, which is my f of xi, for each one. And then here we're going to have, I can take this out because it's the width is going to be consistent as 1/2 for each of them, and then I'll get my f of x1 in this case, and I will substitute these in, right, plus f of x2 all the way out to your f of x6 right here. And this will be 1/2, and this will be f of, on the first one will be 3 over 2, right, 1.5, plus f of 2, plus f of, this will be 5 over 2, plus f of 3 plus f of 7 over 2 plus f of 4. And cleaning this up, you'll end up with, this will be 3 over 2 cubed plus 2 cubed plus 5 over 2 cubed plus 3 cubed plus 7 over 2 cubed plus 4 cubed. And saving you the step in between, the area will end up being 1287, approximately 1287 over 16 square units. Will this be an over or underestimate? This will be an overestimate. Okay, let's take a look at the next one. So for number 3, it says find the exact. This time we need to get the exact area under the curve of that from 0 to 1. Okay, so we know what it looks like, but we have to do exact, which means we have to do the summation methods that we talked about. So let's find delta x again to begin with. On this one, delta x will be b minus a over n, which hasn't changed. But this time I've got a and b, and I don't have an n. Okay, so this is going to be 1 minus 0 over n, which will just give me a 1 over n width. Now, I'm going to choose to do left endpoints, and I'm going to tell you on this particular problem, left endpoints is a little bit easier. So, since I'm doing left endpoints, I'm going to start at x sub 0. That's going to be 0 when I plug it in. Then x sub 1, in my particular case, will be 1 over n. Then x sub 2 will be the previous one, just like we do with our summations, which was x sub 1 plus your delta x. So that means x sub 2 really is the 1 over n plus your delta x, which was 1 over n, which gives us 2 over n. Okay, then we've got x sub 3 over here, and that's going to be x sub 2 plus delta x. And what was x sub 2? Well, we said it was 2 over n plus my 1 over n, and you should start seeing a pattern here, which is going to give me 3 over n, right? And so on. So do you see the pattern? Basically, I'm getting my I over n in this case. So x sub I will be my I, whatever iteration I'm on, over n. So we can use this in our formula. So the area will be approximately a sub n, right? And it's going to be the sum from I equals 1, in our case, to n, and I'm calling 1 f of 0 in my case. And this is f of x sub I times my delta x. This is my width, and this would be my height right there. Right? And so in this, when we substitute it in, we're going to get the sum from I equals 1 to n, and this will be f of I over n times my delta x, which is 1 over n, and I can take the 1 over n out. But I'm going to hold off on doing that just for a minute here, just so that I can continue on. And so I'll end up with the sum from I equals 1 to n, and I'm going to substitute this one in right here into my equation. So that will end up being 2 times I over n minus 2 times I over n squared, right, times this 1 over n that I have out here. All right, let's see if we can clean this up a little bit at this point, and I'll continue on down here. A sub n is approximately the sum from I equals 1 to n, and this will be over here 2 times I over n times 1 over n, and look what I'm doing, minus, I'm going to distribute this summation, minus the sum from I equals 1 to n of 2 times, this will be I squared over n squared, times my 1 over n. And then I can take some things out. I'm going to take out a 2 and an n squared. So that's what they have in common there. That's what I'll take out. And this will be the sum from I equals 1. That's why I weighted from I equals 1 to n of I minus 2 over n cubed. So that's what this first part had in common, right? 2 over n squared. And the second part will have in common 2 over n cubed is what I could take out of this, because that's my constant in the summation, is what I'm trying to say. So this will be the sum from I equals 1 to n, and then I end up with just this I squared right here. Well, we've got formulas. The formula for I, right, is n for the summation of I is n times n plus 1 over 2. The summation for I squared, that formula I showed you before, is n times n plus 1 times 2n plus 1 all over 6. So I'm going to substitute these formulas in. So I'll end up here with 2 over n squared, and this formula will get substituted. This will be n times n plus 1 all over 2 minus 2 over n cubed, and I'll substitute that formula in over here, n plus 1 times 2n plus 1 over 6. And cleaning all this up, I can see if I can find a common denominator, do all that good stuff. So I'll end up with n plus 1 over n. Again, I'm just trying to combine these and clean this up. At this point, I'm just going to go ahead and write one of these goes with one of those, this goes with one of that, and that's how I ended up with n plus 1 over n. Over here, I'm going to do that and that. Two of these with one of those, so that'll be n squared right there on the bottom. So I'll end up with n, so this is minus, this will be n plus 1 over 2n plus 1 all over my 3n squared, which is what's left on the bottom. All right, I'm running out of room, so let's see if I could squeeze this in. We are going to find a common denominator in this case, and that'll be 3n squared. And the numerators will be 3n times n plus 1, and on this side it hasn't changed at all. It's going to be n plus 1 times 2n plus 1. And then this ends up equaling, I'm going to skip a step here. Well, I can put this step, 3n squared plus 3n minus 2n minus 3n minus 1 all over 3n squared, and that comes out to be n squared minus 1 over 3n squared. So what do I need to do with this? Now I need the limit as n goes to infinity of this area, and this is my area sub n. So I need it as n goes to infinity, and I will get 1/3, right? Because this right here will reduce out to give me that 1/3. And that's my limit, and that is the exact area that is underneath this curve. All right, so moving on to number 4. It says, find the exact area of f of x equals x cubed on the interval from 1 to 4. Use left endpoints when setting up the problem. So again, we're going to go with left endpoints here. And we have our equation, and we need the exact area. We know what x cubed looked like. It was the problem up above. And we're on 1 to 4, though. So let's first start out by finding delta x, b minus a over n. Here's a, there's b, so that's 4 minus 1 over n, because we're generalizing it, so I have n, 3 over n as my delta x. Now remember, left endpoints, so really I have x sub 0. That's going to be 1. And just like up above, if you called it x sub 1, but it's really shifted over to the left. Okay, then we have x sub 1, which is this initial value of 1 plus my delta x sub 1, right, my delta x, I should say. Then, that should be a comma, then x sub 2, which would be my x sub 1 plus delta x, and so on. So let's see if I can clean this up a little bit. I know my x sub 1 is going to be this 1, plus I know what my delta x is, that's 3 over n. So x sub 2 would be 1 plus 3 over n plus another 3 over n, which would give me 1 plus 2 times 3 over n. I'm writing it this way so you could see a pattern. Then I can move on to x sub 3. X sub 3 would be this previous one, 1 plus 2 times 3n, plus my 3 over n, which would give me a value of 1 plus 3 times 3 over n. Do you see what's happening here? You see the pattern? This one's just changing for each one. It's 1 over 1, then 2, then 3 for each iteration. So that means my x sub I will end up being 1 plus whatever I you have right here, this is where I substituted in, times 3 over n. So then my area sub n would be the sum from I equals 1 to n of f of x sub I times my delta x, like we've always done. Again, this is your width, this is your height. So width times the height. And then I can substitute some values here. I equals 1 to n. And this is f of this 1 plus I times 3 over n, like that, times my delta x, which is 3 over n. So this becomes the sum from I equals 1 to n of 1 plus I times 3 over n. This is cubed times 3 over n, because I put it into my equation right there. And cleaning this up a bit, I'm going to do something here. This 1 plus 3 over n cubed, oops, I need an I right there. If I work this out, this ends up, and you can FOIL it out, this ends up being 1 plus 9 over n times I plus 27 over n squared times I squared plus 27 over n cubed times I cubed. Okay, FOIL that out and you'll get that. So a sub n is going to be the sum from I equals 1 to n. And now I'm putting all of this in, and you end up with this in here times the 3 over n. And now doing your summation, you'll end up with n plus 9 over n times, and I'm putting in the summation formulas, right? The summation of 1 right here, when I take this, is just the n, okay? And the summation of, this is 9 over n, the summation of I squared would be n times n plus 1 over, or summation of I should say, over 2, plus, then I've got 27 over n squared. The summation of I squared is our formula, n times n plus 1 times 2n plus 1 over 6 plus 27 over n cubed, and the summation of I cubed is n squared times n plus 1 over 4. This is actually squared here. And then I've got this 3 over n still on the outside right here. This one right here. Okay? And all I did at this point was put the summation formulas for each one of these. So summation of I is n. Summation of 1, sorry, is n. Summation of I is n times n plus 1 over 2. That's this summation, and that's the summation from the formulas page I showed you. Now, let's see if we can somehow clean all this up. So, cleaning all this up, I will get the area equals 3 over n times n plus 27 over 2 times n plus 1 over n plus 27 over 2 times n plus 1 times 2n plus 1 over n squared plus 81 over 4 times n plus 1 squared over n squared. I need to take the limit as n goes to infinity of all of this. So this will end up being 3 plus 27 over 2 plus 27 over 2, and now I'll get times 2 here, plus 81 over 4, because that limit will just be 1. Adding all this up, I'll get 255 over 4 square units. All right, let's see. That's a tough one. That was a tough one. Let's see what we got next. We got that we're going to do here. So let's take a look at this number 5 one. And it says find the area of the region y equals x squared bounded by negative 2 to 2. Okay, so if I quickly sketch a graph of what we're looking at here for this particular one, I've got negative 2 here, and it's y equals x squared, so here's at negative 2. And there's 2. I'll have a value here of 4 for each of them. And at 0, it goes like this, right? At 0, it'll come down here through 0. Delta x will be b minus a over n. So in this case, it'll be 2 minus negative 2 over n, which is 4 over n, right? There's my a, there's my b. And it didn't specify. Let's go ahead and do right endpoints this time. So if I do right endpoints, my f of x sub I will be this negative 2 plus my I delta x squared. Now let me explain that to you over here. I went negative 2 right here plus my I if I did the right endpoint. So that would put me like right here somewhere, and that would be my first rectangle, for example. So that's why it's negative 2 plus whatever iteration for each rectangle you made. So continuing on with this, my sum will be, the area will be the sum from, and we know that it's going to be delta x times my f of x sub I, right? This is my width again, this is my height. I wrote it a little bit different this time, it's fine. So this will be the sum from I equals 1 to n, and it'll be this delta x, this delta x times 4 minus 4i delta x plus your I squared delta x squared. So what I did was I obviously put this in here, right? F of x sub I, which ended up going here when I FOILed it out. And so now this is the approximation for my area. The area sub n is going to be, I could take this 4 over n out right now, 4 over n, and I'll have the sum from I equals 1 to n of, this becomes 4 minus 4 over I times this 4 over n plus I squared times my 4 over n squared. And remember, if I take the sum of a constant, it's just going to be n times that constant. So because what I'm going to do now is I'm going to take these summations. So this becomes 4n. So I have 4 over n. This becomes minus 16 over n, and the summation of I ends up being n times n plus 1 over 2. Plus, over here this is 16 over n squared, and the summation of I squared ends up being n times n plus 1 times 2n plus 1 all over 6. So that's those summations. So then let's see if we can continue working this out. This becomes, the limit is what I need as n goes to infinity of this area. Now over here you'll see that these reduce, right? And the limit will just be 16. So I can put that in 16. On the next one, when I distribute, I'll get 32, and then the n over n squared, but then I have n squared on the top. So I end up with this reducing with one of those, and then 2 times the 16 is where I got that 32. Okay, so that's my 32 plus, I'm skipping a couple steps here, but I'm trying to show you how I'm getting about these. This 4n times this will be n cubed, 4 times the 16 divided by 6, and this 2 times the 2 on top, because on the top here I'll end up with n, and then n cubed. They will reduce out. If you want, go ahead and show that extra step. I know I'm skipping it right here, but it'll help you out if you write that step in between, this distribution step and finding the limit of it. But that's what you should end up with, and you end up with 16/3 square units. Again, all I did was distribute here to each of them, and in that summation formula as I plugged in infinity. All right, so now for number 6, it says set up but do not evaluate. The area under y equals sine x from pi over 2 to 2 pi. So what I'm looking at is a curve that looks like this, right? From pi over 2 is where I'm going to 2 pi right there. So we know that this curve will go up, reach its maximum right here, come down through pi, and then go like that, right? So we can say that delta x, b minus a over n, and in this case it's going to be 2 pi minus pi over 2 over n. And we can clean this up, and this will end up being 3 pi over 2 over n, and I can rewrite this as 3 pi over 2n. And then we have to take a look at what our f of x sub I is, and that's our equation, and this will be the sine. And now since I'm going to go ahead and plug this in, I'll have my pi over 2 starting point, but I'm going to shift this over. So if I do this with the right endpoints, we're going to say that that's going to be the pi over 2 plus my I delta x. If I do left endpoints, I will end up being 0, my starting point. So it just depends on how you want to do that. Okay? And looking at this, remember here, like I just said, x sub 0 is pi over 2, and delta x would end up being this, whatever, if I wanted to start with x sub 1, say, this would be pi over 2 plus my delta x. X sub 2 would be this, continuing on, so x sub I would end up being pi over 2 plus my I delta x. That's how I got that. And that would shift me over if needed, or if I just start at 0, my I would end up being 0 there, if I wanted to do it that way. All right, so now, plugging all this in, I will have the area, right, is the limit as n goes to infinity of this summation, where I is equal to 1 over n, and now I'll have this 3 pi over 2n. This is my delta x, this is my width, times my height, and my height in this case will be this sine of pi over 2 plus my I delta x. Now, it said set up, but do not evaluate, so we can leave it at this point, because if we had to evaluate it, we would be plugging in that I. If you were solving this completely, you would have to use this sine x plus y, that situation, to work it out, just on a side note here, and you'd have to use that, from trig, your identity, and this would end up being sine x cosine y plus cosine x sine y, like that, and work it out that way. Things would reduce a little bit, but still, because when you have pi over 2 over here, you'd end up at 0, so it would reduce a little bit, but it's still going to be a complex problem. So you could, for all purposes for this class, leave it like that, because even when you do reduce it, it's still very difficult to do by hand. All right, so we will stop there. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.